Hello and welcome to this module 9 of the course Design Practice 2. We were talking and discussing about Bezier curves and the way you can fit the curve typically starts from the first and passes through the last point, but there are certain other control points which fall within the ambit of these 2 points which define how the curve geometry would be. And then if supposing those control points are changed and their positions are changed, the geometry varies suitably based on that change. So, let us actually now try to plot practically from a Bezier standpoint. We have these 4 different control points in a particular example V1, V0, V1, V2 and V3 and they are on a 3-dimensional plane. So, these are 3-dimensional coordinates with a unique value for x, y and z respectively when we vary between the different points, and we want to develop the Bezier curve equation keeping these control points in view and also try to further fit the curve for values of t equal to 0, 1/4, half, 3/4 and 1 and plot the curve. Okay. So, it is like a complete treatment as we did in case of Hermitian for the Bezier function. So, we want to start this curve plotting exercise from the equation on Bezier curve because the number of control points is 4. So, n becomes equal to 3, you know that n plus 1 control points are there, n plus 1 equal to 4. Okay. So, the curve function that would happen because of that looks something like I varying from 0 to 3 factorial 3 by factorial I factorial 3 minus I t to the power of I 1 minus t to the power of 3 minus I V I, where V I is the number of control points. The number of control points you know are V 0, V 1, V 2 and V 3 respectively 0 to 3. So, I varies in that manner, and so if I wanted to actually try to write this in algebraic manner, this V t would look something like V 0 1 minus t whole cube plus 3 V 1 t times of 1 minus t square plus 3 V 2 square of t times of 1 minus t, I am sorry, plus 3 V 3 times of t cube. T of course, we vary between 0 and 1, that is how the parametric form of equation is defined. And we now start substituting the different values. You know that there are all different x, y and z coordinates in case of these values. This is, I am sorry, this is not 3 V 3, but just V 3 T 3 T cube. So, when we substitute the x values, y and z values respectively, and for the different values of t that have been given in the question, namely 0, 1/4, half, 3/4 and 1, we want to find out the different points of this Bezier curve, which will give you an idea of how the curves would pass through, or what points the curves would pass through in space, where the first and the last points are similar to V 0 and V 3, but the in between points may typically be different than the points which are there actually on the Bezier curve. So, let us algebraically, let us numerically try to solve this example here. Let us say when we do for V 0, you know that V 0 has coordinate value which is given by 0 0 0, because this is the first point, and typically the Bezier curve's first point also passes through the point which is outlaid across both ends of the curve, that is V 0 and V 3 in this particular case. So, we know V 0, we need to find out what is V 1/4, and for doing that we first put only the x values. Okay. So, we now split this up into 3. So, you have a V x of 1/4, you have a V y of 1/4 and you have a V z of 1/4, and all of them are amounting to solving the equations with different substitutions for V 0, V 1, V 2 and V 3 and so forth. We know that the values of V 1 are 0 2 0, that of V 2 are 4 2 0 and that of V 3 are basically 4 0 0. Okay. So, the V 3 here in this case in any event is going to be 4 0 0, which is corresponding to, I am sorry, this is V 1. Okay. So, that means corresponding to t equal to 1, this is necessarily where the curve should pass through, and let us look at what are the V x, V y and V z's. So, we take the x value of V 0 being equal to 0 0 0. Okay. So, 0 times of 1 minus t cube. So, when we are talking about 1/4, this is 1 minus 1 by 4, that is 3 by 4 cube, plus thrice the x coordinate of V 1, which is 0, again times of the value t times of square of 1 minus t. So, you have both these terms eliminated because of being multiplied with 0. The third term has a 4. So, V 2's x coordinate is 4. So, 3 times of 4 times of square of t, which is 1/4 square, times of 1 minus t, which is 3/4, plus 3 times of again the value of the x coordinate 4 times of 1/4 cube. Okay. So, that is how the V x 1/4 happens to be, and this can be calculated as, in this particular case, 5/8. Okay. So, let us, if we just calculate V x 1/4, this is 5/8. Similarly, if we wanted to put all the y values here, so obviously the first two terms would, or first term would be 0 in that particular case. Okay. Times of, so V 0 is 0 for all the 3 coordinates. So, we are now calculating y. So, we put the y equal to 0 value here, times of 1 minus 1/4 cube, plus again 3 times of 2 times of 1/4 times of 3/4 square, plus 3 times of, in this particular case the value happens to be 2 times of 1/4 square times of 3/4, plus again so I am sorry, this is not, this happens to be only coefficient 1, not 3. Okay. So, so times of V 3, which in this case, in this particular case is 0. Okay. Y corresponding to the point V, the last point V 3 is actually 0 times of 1/4 cube. Okay. So, this becomes equal to 9/8, and similarly, if you wanted to look at zeros, we know that all these values here V 0 to V 3 are being 0. So, it becomes 0. So, if I wanted to describe the coordinate of V 1/4 in space, this can be written down as 5/8, 9/8 and 0. In a similar way, we can do this for V half, and for the V half the equation happens to be 1/8 of V 0 plus 3/8 of V 1 plus 3/8 V 2 plus 1/8 V 3. I am calculating pretty much in a similar way by substituting all the values of t corresponding to half in this particular expression. Earlier it was 1/4, and so in that event, if I put the different values of V 0 to V 3 in the x, y and z directions, we get again another 3 set of coordinates 2, 3 by 2, 0. And similarly, we could do the same for V 3/4, where the final formulation would be in the manner 1/64 V 0 plus 9/64 V 1 plus 27/64 V 2 plus 27/64 V 3, and then if we substitute again x, y and z values of all these 4 different points, we are left with coordinates 27/8, 9/8 and 0. So, we have now plotted whatever falls on the curve. These again, for the illustration of all readers, are basically the points which are control points. The curves will not pass through them necessarily, they will only pass through the endpoints, but in order to define the Bezier function, etc., they are absolutely necessary. But when the Bezier values actually prop up, they correspond to the values taken by different values of t, that is 1/4, half and 3/4, and when we solve these problems, we get a set of coordinates here, all in 3 x, y and z directions, corresponding to the different incremental t, okay, which is there in the parametric form of the equation. So, if I plotted all this together on x y plane, x y z plane, obviously one thing that is being seen here is that whether it is V 0 or V 1/4 or V half or V 3/4 or V 1, all the z values are 0. So, therefore, it is essentially an x y plot. Okay. There is no plot along the z direction. That is how the problem has been defined in this particular case. But if I wanted to plot these values together, 5/8 happens to be about 0.6, 0.63, and 98 happens to be 1.12 or 125 maybe, and similarly this is 2 1.5, this is again 3.7 1.120, and with all these plots here we would be able to get sort of a circle, okay, in this manner, where we are talking about the first point which is 0 0 of course, the last point which is 4 0, and in between there are a set of points here. One of them is being described by 0.63 along the x direction, 0 along the y direction, and 1.12. So, somewhere here maybe, let us say we have a scale that we want to plot in a manner, so that you have 1, 2, 3 and 4. Okay. So, these are the different values starting from 0, and similarly we have another scale here. So, you have 0.2, 0.4, 0.6. Let us actually plot this figure with respect to the scale that I have drawn, 0.8, so on and so forth. So, here we are talking about a y increment of in this particular case 1.12 and an x increment of 0.64. So, corresponding to somewhere here, the curve somewhere here. So, we are talking about this kind of a curve, okay, starting from here. Then the next coordinate corresponding to v half is 2 3 by 2. So, 2 and then 1.5. So, somewhere here, okay. So, passing through this, and then again 3.7 1.12. So, similar level, but again 3.7 is somewhere here. So, again somewhere here, okay, and then finally 4. So, that is how the curve is going to be placed. So, it is like a, if I looked at the geometry, it is going to be like an arc, okay, in this manner, and that is how the Bezier curve would look like typically in this particular case. So, the Bezier curve is defined by now a polynomial or polygon described through connecting all the different coordinates, and if I looked at whether the condition of the Bezier is being set here, namely the first point would align with the tangent. So, the first line segment of the polygon of a curve would line with the tangent to the first point, and the last line segment would line with the tangent to the last point. So, it is actually true in this particular case, because when we start with the different points, control points, you have 0 0 here, then 4 2. So, 4 2 is something like, I am sorry, 0 2, 0 2 is something like here, okay. So, we are talking about a point somewhere here as v 1, this is v 0. Then similarly we have v 2, v 2 is corresponding to 4 2. So, somewhere here again 4 and 2. So, this is v 2, okay. So, we join these 2 points, and then finally v 3 to v 4, okay. So, this is the polygon which we are creating with respect to this Bezier curve, and as you see here, the tangents of the first and last points are parallel to the line segments which define the polygon, which is going to define the curve. So, in a way, that is how Bezier curve is defined. So, practically you have now seen how different fits like Hermitian as well as Bezier curves are lined. We can actually try and look at some other varieties of what are the essential differences. So, we have different curve fitting geometries like the B-spline fit, the rational B-spline, the non-uniform rational B-spline curves. The B-spline is considered a generalization of the Bezier curve. Local control is an interesting feature in such a B-spline plot or B-spline curve. It implies that any change in the local control point affects only that part of the curve. So, therefore, just as in the Bezier you saw that if even one of the control points vary, the overall shape and feature of the size of the curve changes. In this particular case, if a single point varies, it only concerns the overall curve variation to be in that particular segment of the polynomial which has that particular point, okay. So, you can locally vary rather than globally varying the whole curve, as was the case for the Bezier. So, there is a further degree of control that can be given through rational B-splines, which are a sort of a generalization of B splines with an added weight. So, now each section would have a different weight. So, if I wanted to vary one section and typically I can put a higher weight to that. So, a little bit variation in the control point would give a lot of variation in that particular section and vice versa. So, that is how you have the different features of curve fitting in 2D plane. We will go to a little bit interesting a different dimension altogether of the problem, which is about surface modeling. So far you have been looking into how two dimensional curves, which would get into organic two dimensional forms, let us say, would be able to get created in terms of data structure within a computer. Now, looking ahead, I am going to talk extensively about how given a particular curve or given a set of different curves, how can we align them together or integrate them together to form a surface. Because so far, even if with line geometry or even with, let us say, the wireframe model, we are able to define the overall shape and feature, it is very difficult to see how the surface behavior would happen, particularly in 3D solids. And when we are talking about organic solids or organic shapes, even the complexity is much higher. So, we need to one option is, of course, we need to represent, but another option is how we actually do a data structure, so that it can be used for representation. So, we are talking about slightly higher order analysis in comparison to just merely representation of shapes or three dimensional objects through textures and lines. So, let us go to surface model. So, in a wireframe modeling, we take advantage of the simplicity of certain surfaces. For example, a plane is represented by its boundaries. We say nothing about the middle of the plane, neither we have a data structure for that, but now we would like to do that through this approach of surface modeling. So, further to add complexity, we know that shapes of cars and aircrafts are not that simple, and particularly ships also are very complex, and so they do not consist of simple geometries anymore, and so representing only the whole feature with boundaries is not really a very good idea, particularly when we talk about creating a data structure, so that a three dimensional plane can be seen. See, visualization generally has been enhanced because of the CAD technology. So, therefore, why not utilize it fully is the next question, and so a complex data structure needs to be developed, so that you can plot that in terms of a surface with control of each and every point on the surface that we are constructing. So, surface modeling systems contain definitions of surfaces, edges, vertices. It contains all information that a wireframe will not provide, and in addition it also contains information of how two surfaces would connect to each other. There are certain entities which can be defined. For example, a plane surface could be defined with 3 lines most simplistically, or maybe multiple lines, as you are seeing in this particular figure. So, if 3 points which are non-coincident are in space in near proximity to each other, it automatically defines a plane which passes through all the 3 points. There can be surfaces descriptions in regular geometries through ruled surfaces. So, typically a ruled surface can be defined as a linear interpolation. So, there is curve 1 and curve 2 in this particular case, and you are having some rulings or some lines in between to connect the curves or multiple points on these curves, so that you can have a set of plane surfaces which would be able to approximate the whole surface which is being formulated by the curve. So, informally, the straight lines connecting the 2 rails would form the surface. There can be surface of revolution created. For example, there is a line which sweeps in plane across another line at a certain angle. If it sweeps on a full rotation or half rotation, it also creates a surface generated by rotating a planar curve in space, and that can be a straight line or any other curve at a certain angle. You also have tabulated cylinders. So, in this particular geometry, we are considering the surface to be generated by sweeping a planar curve in space in a certain direction at a certain distance. For example, above a straight line sweeps, for example, sweeps in a rotational manner, and it sweeps about a path which is circular in nature with the center. So, typically the straight line would then be called the generatrix, and the circle would be called the directrix, which generates the straight line to move along the circle, thus formulating a surface. We also talk about Bezier surfaces or B-spline surfaces, which are slightly complex. They are not that easy as the regular surfaces has been shown in the last 3 examples here, 4 examples here. So, they are actually irregular surfaces, okay. And so, when we come to irregularity and we come to patches which are formulated through multiple data structures, probably with the Hermitian fit in mind or with, let us say, the Bezier fit in mind, it is very obvious. So, this whole patch is created with the goal of trying to fit on a complex profile, so that we can get the extract of the data, okay, of that surface through predictive modes once this fits very well with the profile itself. And instead of going for a sort of a 2-dimensional space curve, we are talking about a surface. So, therefore, obviously, the degrees of freedom would increase in that case, and because of the degrees of freedom increasing by 1 order, there would be a variety of complexity created which would be needed for maintaining and creating such a data structure. Let us look at one problem example here when we talk about again how to represent surfaces in terms of implicit and explicit equations. Okay, so, because there is a third dimension involved and degree of freedom is increased by 1, we would like to represent in an implicit manner a particular surface through an equation f x y z equal to 0, a function of x, y and z altogether equal to 0. It will define geometrically a locus of points that satisfy the constraint equation, okay, and that those locus of points, if plotted in a 3-dimensional space, would result in what we know as the surface. So, what it basically means is that you have 2 variables in this particular way, x and y, and we are representing through a function f x y z equal to 0, a sort of a relationship which is inbuilt, and it has to be found out. So, we call this, let us say, capital Z x and y. So, the whole third dimensional z is defined by different values of the variables x and y. So, the same thing can be written in explicit form. Remember, in the curve case we had talked about 2 different equations for example, how x would be independently related to y and z, because in this case, in that particular case, both y and z were dependent variables where x was the independent variable. In this particular case, it is that both x and y are the independent variables, degree of freedom is increased by 1 and z is the dependent variable. So, we can describe the same equation in a very explicit manner, in a very direct manner, by saying that v the locus of all points v in space would be represented as x, y and function of x, y, which is actually the z value. So, here the function is very clear, you do not need to calculate as you need to do from this extract here, okay, and so that is why it is called explicit. So, when you compare the equations for a 2D curve and a 3D surface, the only difference between a space curve and a surface mathematically is that points on a space curve are defined by a single degree of freedom and that on a surface by 2 degrees of freedom. Remember, new variable y has been added into the x variable which was otherwise used for describing the space curves. So, that is the whole difference which happens in case of a surface. This, for example, is a representation of a surface. So, usually an arbitrary surface in x and y could be defined with a functional relationship f x y equals the third dimension z, and it can be again mapped with an xy grid where we have independent values of x and y, and corresponding to each value or each combination of x and y we plot a z value. Okay. So, there are exactly p plus 1 and q plus 1 points in the x and y grid, one in the x direction, one in the y direction, to define a set of points which would be able to finally formulate the surface. So, we would like to now probably at some next module consider how to represent such a surface mathematically. I would like to just do one case of a Hermitian surface or a Hermitian patch, and the idea is that a Bezier patch can be an extension of what I do for the Hermitian. The computations will become extensive because obviously the data structure now has one completely new degree of freedom which adds up. So, there are different combinations and combinatorials which will be formulated between the x and y, so that there can be a z value which maps the surface. So, we will do this in the next module. I am going to close this module in the interest of time. Thank you very much.